now we will draw the PV diagram for this Otto cycle according to the working of this SI engine. So, we are having the pressure in the y coordinate, volume in the x coordinate. Initially the piston is at BDC, as you can see here. Initially the piston is at BDC and the volume inside the cylinder is nothing but the clearance volume. Here I can show this point with 0. The volume here is the clearance volume. Now, as the piston moves from TDC to BDC, you can see the volume inside the cylinder is increasing. The pressure is almost constant. Here, as I told you, we are discussing the ideal Otto cycle only. The pressure is almost constant, the piston is moving from TDC to BDC, volume is increasing. Okay, so, it will travel from 0 to 1. Now, after that, this was the suction stroke. Now, second stroke is the compression stroke. The inlet valve is now closed and the piston will travel from BDC to TDC, and ideally this compression is assumed to be a reversible adiabatic compression process. Okay, so, we are having a reversible adiabatic compression now, and at the end of this compression the piston will travel from BDC to TDC. The process here is from 1 to 2. Then after that we are having the spark plug will produce a spark and the heat is added to that fuel air mixture, or that fuel air mixture will be combusted. And as I told you, that heat addition is at constant volume. We assume that heat addition in the ideal Otto cycle is at constant volume. So, we are having a constant volume heat addition process. Okay, so, from 2 to 3 is a constant volume heat addition process. Then after heat is added, then it will expand, and then that expansion ideally again is assumed to be a reversible adiabatic expansion process. So, 3 to 4 is a reversible adiabatic expansion process. Okay, and the piston in this expansion process will travel from BDC to TDC. Now, at the end of this expansion the heat will be rejected, and that heat rejected is again at constant volume. Okay, so, heat rejection at constant volume from 4 to 1, and after that the exhaust stroke, the piston will move from BDC to TDC, the flue gases will get exhaust. Okay, so, here the piston will again move from point 1 to point 0. Okay, so, this is the whole Otto cycle. 0 to 1 is the suction stroke, 1 to 2 is the compression stroke, 2 to 3 is a constant volume heat addition, 3 to 4 is a expansion stroke, 4 to 1 is a constant volume heat rejection, and then from 1 to 0 is again the exhaust stroke. So, this is the whole Otto cycle. Now, here you can note one thing, that ideally we are assuming the reversible process. All processes are perfectly reversible. So, during that reversible process, the path which is travelled during suction stroke and exhaust stroke will remain same. In actual cycle, obviously this path is not same, they are different path due to irreversibilities, but in ideal cycle, because of reversible processes, the path which is travelled from 0 to 1 during suction stroke, same path will be travelled from 1 to 0 during exhaust stroke. That means the work which is done by the system, by the engine during 0 to 1, the same work has to be done on the system, on the engine from 1 to 0, and that work will be cancelled out. So, we can eliminate this 0 1 line, getting this, because we assumed it to be a reversible process, and from 0 to 1 and 1 to 0 positive work, negative work will get cancelled out, and finally, we will get the cycle as 1 2 3 4. This is our final Otto cycle. We will consider this cycle as the final ideal Otto cycle. 1 2 is a reversible adiabatic compression, then constant volume heat addition, then reversible adiabatic expansion, and then the constant volume heat rejection. This is whole Otto cycle. Now, similarly, we can draw the TS diagram for this. 1 to 2 is a reversible adiabatic compression process, which is an isentropic process. Reversible adiabatic process is an isentropic process. So, in TS diagram, we will be having the vertical line. Then 2 to 3 is a constant volume heat addition. So, we are having a constant volume process in 2 to 3. Then 3 to 4 again a reversible adiabatic, a vertical line, and then 4 to 1 is a constant volume heat rejection process, constant volume curve as we know in the TS diagram. Okay, so, these are the PV and TS diagram for this Otto cycle. Okay, so now coming to the efficiency of this Otto cycle. So, as we know, efficiency is W net by Q1 or Q1 minus Q2 by Q1, or you can call it as 1 minus Q2 by Q1, where Q1 is heat added and Q2 is heat rejected. Now in this Otto cycle, as we know, heat addition takes place in the process 2-3, which is a constant volume process. So heat added at constant volume is, as we know, is mCv del T. So this Q1 will be equal to mCv into T3 minus T2. Heat addition process in the heat addition is at process 2-3. Now similarly, this Q2 is at process heat rejection is in process 4-1. So this Q2 will be equal to mCv T4 minus T1, since this is again a constant volume process. Okay. Now process 1-2, as we know, is the adiabatic compression process, and in this adiabatic compression process, as we know, T2 by T1 will be equal to V1 by V2 to the power gamma minus 1. And what is this V1 by V2? V1 is the maximum volume, as we see, and V2 is the minimum volume, or you can call it as clearance volume. So this V1 by V2, the ratio of this V1 by V2 is nothing but compression ratio, as I have told you, maximum volume of the cylinder to the ratio of maximum volume to the minimum volume of the cylinder is nothing but the compression ratio. So this V1 by V2 is nothing but Rk. So you can say this T2 by T1 is equal to Rk to the power gamma minus 1. Now similarly, in process 3-4, this is again a reversible adiabatic expansion process. So in this process 3-4, again T4 by T3 will be equal to V3 by V4 to the power gamma minus 1. And V3 here is equal to V2, since process 2-3 is a constant volume process. V4 is equal to V1, since process 4-1 is a constant volume process. So this can be written as V2 by V1 to the power gamma minus 1, or Rk to the power gamma minus 1. Now from these two equations, this T2 by T1 will be equal to T3 by T4, or you can say T4 by T1 will be equal to T3 by T2. Okay. Now coming to the formula for efficiency, eta is equal to 1 minus Q2 by Q1. Q2 is mCv T4 minus T1, and Q1 is mCv T3 minus T2. mCv will be cancelled out, and we will get what? 1 minus T4 minus T1 divided by T3 minus T2. Now from numerator, where we are taking T1 as constant, we will get what? 1 minus T1 into T4 by T1 minus 1. From denominator, taking T2 as constant, we will get what? T2 into T3 by T2 minus 1. Okay. And since this, since this T4 by T1 is equal to T3 by T2, which will be cancelled out, and we will get efficiency as 1 minus T1 by T2. And as we know, T1 by T2 is equal to V2 by V1 to the power gamma minus 1. The compression ratio Rk is V1 by V2. So this will be equal to 1 minus 1 by Rk to the power gamma minus 1. So this is the efficiency of Otto cycle. Efficiency of Otto cycle, eta is equal to 1 minus 1 upon Rk to the power gamma minus 1. Very important thing, very important formula. Okay. So from this efficiency, you can see that this efficiency depends on two factors. First is the compression ratio, and second is the gamma. Now what is the effect of this compression ratio? So as the value of this compression ratio Rk increases, 1 by Rk to the power gamma minus 1 will decrease, 1 minus 1 by Rk to the power gamma minus 1 will increase. That means the efficiency will increase. So as the compression ratio increases, the efficiency will increase. So this is the one way to increase the efficiency, but is it the effective way? Because after increasing the compression ratio beyond a certain level, what will happen is it will cause the pre-ignition and knocking. Now what is this pre-ignition and knocking? If we are increasing the engine size beyond a certain level, what will happen? The pre-ignition will occur. Now what actually is this pre-ignition? Pre-ignition आखिर होता क्या है? So suppose in order to increase the compression ratio, we are increasing the size of the engine beyond a certain level. Now what will happen? Because the size of engine is big, now when the spark plug is producing spark, now what will happen? The combustion process will be carried out slowly throughout the engine, throughout the cylinder of the engine. Now before the combustion reaches the other end of the engine, the temperature of the other end is increased beyond the ignition temperature of the fuel, and it will catch fire. That means combustion process हो रही है, combustion process is getting carried out throughout the engine. Now before कि वो combustion process पहुँचे cylinder के end point तक, वहाँ पर temperature उसका increase हो जाता है and it catches fire. That means दो point से combustion ignition चालू हो गया है, and then what will happen? Then they will collide with each other, you can say, and they will produce some turbulence, and because of that the knocking phenomena will occur. Okay, so this process is called as pre-ignition. जो time के पहले ही जो ignite हो रहा है, that process is called as pre-ignition, and as a result of that pre-ignition, knocking sound is produced. This phenomena is called as knocking, and because of that knocking, because of this pre-ignition, detonation of the engine is occur. Okay, so this actually is very dangerous for the engine. So instead of using a single big engine, we always try to use multiple engines. So जैसे कारों में अगर हमने देखा in which we have to use 1200 1500 cc engines. So in that, instead of using a single engine, we try to use 4-cylinder engines. ट्रकों में, बसों में we use 16-cylinder engines. So okay, so wherever more volume of the engine is required, instead of using single cylinder, we use multiple cylinders just to avoid this pre-ignition and knocking phenomena. और सिंगल सिलेंडर में भी एक लेवल के ऊपर तक भी यूज़ हुआ है, ऐसा नहीं हुआ है. एंड द टेक्नोलॉजी वाज फर्स्ट इन्वेंटेड बाय द बजाज मोटर्स, जिसने इसका पेटेंट भी कराया था. दैट टेक्नोलॉजी वाज कॉल्ड एज DTSI, digital twin spark. Now what is that digital twin spark? There are two spark plug. Instead of having one spark plug, it gave two spark plug. Okay, so because of the two spark plug, the combustion process starts from 2 points and it is smoothly carried out throughout the engine. ओके, तो इसके कारण प्री इग्निशन अवॉइड कर सकें, हम नॉकिंग अवॉइड कर सकें. दिस वाज कॉल्ड एज डिजिटल ट्विन स्पार्क एंड इट वाज स्पेशली यूज्ड इन द पल्सर बाइक्स ऑफ 150 180 cc ऑफ हायर साइज इंजन्स. देन देयर वाज वन मोर टेक्नोलॉजी अगेन which was bring out by the Bajaj only, that was for Pulsar 220 cc, and the technology was DTS-FI, digital twin spark fuel injection. That means apart from having two spark plug, it gave a fuel injector also. Okay, so that means that the two spark plugs are carrying out the combustion process smoothly. Now in between, the fuel injector is injecting the fuel, more fuel there in that engine. So because of that, more power can be developed. With a small size engine, we can develop more power because more fuel is getting injected in between. Okay, so this is called as DTS-FI, digital twin spark fuel injection. Then there was one more patent taken by the Bajaj, that was DTS-SI. It was basically used in the lower cc bikes, 110 125 cc Discover bikes. SI here stands for swirl induction. Okay, so there is a swirling process during the mixing of that air fuel mixture, and because of that swirling, air fuel mixture mixes properly and there is an efficient, effective combustion of the fuel inside the engine. Okay, so these were the different technologies which were used in order that we can use a bigger engine in a small vehicle, in a small bikes. Okay, so what my point here is that we can increase the compression ratio up to a certain level, but not beyond that level, in order to increase the efficiency. Otherwise there will be the problem of pre-ignition and knocking. So what is the other way to increase the efficiency? So as you can see in the efficiency formula, eta is equal to 1 minus 1 by rk to the power gamma minus 1. So increasing rk was the one way. Another way to increase the efficiency is to increase the value of gamma. More is the value of gamma, more will be efficiency. तो गामा की वैल्यू जितनी ज़्यादा होगी, efficiency उतनी ही ज़्यादा होगी. And as we know that gamma for the monoatomic gas is 1.66, for diatomic gas it is around 1.4, and for triatomic gas it is 1.33. So maximum value of gamma is for monoatomic gas. So using monoatomic gas in an engine will yield higher efficiency as compared to using the diatomic gases. Monoatomic gas, for example, argon, neon. So using this gas, these gases will give us more efficiency than using the air. But still ये gases use करना practically viable नहीं है. Why so? Because we cannot use a cylinder filled with this gases along with our vehicles. Okay, air is obviously easily available everywhere. The engine can easily suck air from outside after filter. Okay, but having the monoatomic gases is not practically viable. But with monoatomic gas, obviously the efficiency of the engine will increase as compared to for using the diatomic gases. Now let us determine the maximum work output for this Otto cycle. Okay, so work output, as we know, is equal to Q1 minus Q2. Okay, Q1 is CV into T3 minus T2 and Q2 is CV into T4 minus T1. Just put the value, we will get what? CV into T3 minus T2 minus T4 plus T1. This will be our work done. Okay, now as we know, in process 2.1, this is a adiabatic compression process. So T2 by T1 is equal to Rk to the power gamma minus 1. Similarly, in process 3.4, T3 by T4 is also equal to Rk to the power gamma minus 1. Okay, so from these two equations, we can conclude that this T2 by T1 will be equal to T3 by T4, or you can say this T4 will be equal to T1 T3 by T2. So we have the value of this T4 in terms of T1, T2 and T3. Now what is the use of this? I will tell you. So work done formula, as we have seen, W by CV is equal to T3 minus T2. Just put the value of T4 here, minus T1 T3 by T2 plus T1. Okay. Now, what we have to do is we have to maximize this work, and in this particular formula we have three different terms T1, T3 and T2. Now, the value of T1 is almost constant, which depends on the surrounding air, the suction temperature. The value of T3 is also constant, almost constant, which depends on the metallurgical condition of the engine, okay, because it cannot be increased beyond a certain limit, otherwise it will harm the engine. So, the only parameter which can be changed is T2. So, what we can do is we can adjust this T2 so as to get the maximum efficiency. So, in order to get the maximum efficiency, what we will do is we will differentiate this with respect to T2 and equate it to 0. Okay, so just differentiate this, we will get what? 1 by Cv dW by dt2 is equal to minus 1 plus T1 T3 by T2. This should be equal to 0. Okay, so from here this T2 will be equal to under root of T1 T3, and similarly you can determine the value of T4 also. This T4 will also be equal to under root of T1 T3. So, just put the value in the formula for work done, and when you put the value of this T2 and T4, these are the conditions for maximum work done. So, when you put this value, you will get maximum work done. So, this W max will be equal to Cv T1 plus T3 minus 2 root of T1 T3. So, this is the maximum work done which we can get in the Otto cycle, Cv T1 plus T3 minus 2 root T1 T3.